Hi everyone, this is Vlad. We'll start in a minute or so, just waiting for David to join.
Hello, everybody.
Hi, David.
Can everybody see and hear me?
Yes.
Can everybody see and hear me? Yeah, I can. Can people just put a... Ah, super, great. Yeah, sorry we're starting this a little bit later. I've just literally got through the door, but we are going to do something really fun today. Surely everybody's favorite topic. We're going to do some Euclidean geometry. I have got a few questions that I want to look at, which are, I think, particularly instructive and cover some Euclidean geometry, which is often missed at school. Okay, so I'm just going to share my screen. And hopefully people can see my screen. So this is a challenging webinar to do because Euclidean geometry, I think, often takes a little bit of processing. But this is the first question which I really want to go through. So it says a quadrilateral ABCD is such that BAC equals CBD equals DCA equals ADB equals 30 degrees. And then it tells me that the diagonals AC and BD meet at A, and it asks me to find the acute angle BEC. So put it into the chat. Okay, what I think it's fairly obvious. What do you think is the first thing that anyone would need to do when faced with a Euclidean geometry problem like this? Okay, I hope that everybody is putting into the chat, okay, draw a diagram, because you can't get anywhere without a diagram. Okay, so I'm just going to draw, I'm going to get my ruler out, and I'm just going to draw a quadrilateral, and it says A, B, C, and let's do 4 sides. This is why this is a challenging webinar to do, because I don't want to sort of have everything pre-built. I want to do it. And then the diagonals meet at E. Okay, so let's let the diagonals meet at the point E. And let's get rid of my ruler. And let's put this information into a diagram. So we've got A, B, C, D. And then it gives me a whole bag of angles, BAC, which is 30 degrees. CBD, which is 30 degrees. DCA, which is 30 degrees. And ADB, which is 30 degrees. and it wants to find the acute angle BEC. So it wants this angle here, 5. As you can see, I've left my dog. Well, you might be able to see. Well, no, sorry, you won't be able to see, but you might be able to hear that when I got home, I just put my dog into the garden. You might hear my dog yelping outside because it's freezing. In the time that it takes me to get my dog back in, I want you to try and see if you can make any observations about this, this quadrilateral, and anything which you feel might be helpful to observe. And I'll give you a clue that when I was preparing this webinar, I was really thinking what sort of thing might be useful to really include in the webinar that people who do Euclidean geometry might not have seen at school. So does anyone have a suggestion of what type of parallelogram no, sorry. What type of quadrilateral is A, B, C, D? Okay. And I'll have to own that Freudian slip. Okay. This quadrilateral ABCD is a parallelogram. Okay, that's why I said parallelogram rather than quadrilateral, because I knew the answer. But why? And this is a big observation, and this is a result which is very, very familiar to you, but in a way, but presented in a way which is not which might be unfamiliar. Okay. What schools are very, very good at teaching is that if we have a pair of parallel lines, okay, right the way back to elementary school, you're probably taught that corresponding angles are equal and alternate angles are equal. Okay. So lines parallel implies alternate angles are equal. But something which schools are maybe not so good at discussing is what is meant, well, is what are called converse results. So in other words, results that go in the kind of opposite direction to one that you might expect. So for example, okay, well, not for example, in this example, okay, is it true, is the result true in the opposite direction that if alternate angles are equal, that implies the lines are parallel? So let's do a little vote in the chat. If you think that this implication is also true, put a thumbs up or a yes. If you don't think it's true, put a thumbs down or a no. So I'm just waiting for the chat to fill up, and in the meantime, hopefully this gives some hint at whether it's is true or not. Oops. Okay. It is indeed true. Okay. And so the shape ABCD is indeed a parallelogram. Okay, and if you didn't make that observation, this question would be difficult. So I'm going to redraw it as a parallelogram. Okay, because an accurate diagram is better than an inaccurate diagram. So we've got A, B, C, D, and E. And we've got 30 degrees. 30 degrees here, 30 degrees here, and 30 degrees here. Okay, and as it's a parallelogram, these diagonals bisect one another. Okay, I'm just going to call an angle something. I'm just going to call this angle here, the one which isn't 30 degrees, I'm going to call it phi degrees. Okay, and if you were to do a little bit of angle chasing, there's a lot of angles which are alternate to phi, like this one over here and so forth. I'm just going to check the chat. Yes. Okay, great. So lots of people put in the chat that yes, it is the case that if alternate angles are equal, then the lines are parallel. Someone put in the chat that they've only just joined. So I'll just repeat the question. So we were given that a quadrilateral ABCD is such that all of these angles are equal to 30 degrees. It then told me that the diagonals met at E, and it asks me I'm trying to find the acute angle here, BEC. So this is the angle that's wanted. And for the person who joined late, the sort of theme of this question, which is going to be a little bit of a theme of the sheet, because I think it's something which is often a little bit overlooked in geometry, is the importance of a converse result. So what I've used here is I've used a result in slightly the opposite order to the one that, or the sort of opposite logical direction that one normally sees it. So normally one is given a pair of parallel lines and says that alternate angles are equal. The key to unlocking this question is that given a pair of alternate angles, like this 30 and this 30, that allows us to conclude that the lines are parallel. And similarly, this pair of alternate angles here and here allows us to conclude that this pair of angles are equal. Okay. Again, it's difficult to resist the temptation to sort of rush. But in the chat, can anyone, and this is a challenging problem, by the way, can anyone suggest a piece of geometry that might be useful to find the angle, well, to be able to find the angle X? So I'll give you a clue. This angle X is an angle which is part of this triangle BEC. Okay, and let's note that this triangle BEC has got angles 30 degrees, X, and phi as its angles. Can anyone stare at this diagram long enough to tell me anything which might be useful? So someone has suggested congruent triangles. Okay, now I'm not, I think there's definitely a triangle that's congruent to BEC. It's just the triangle opposite, it's the AED. But I'm not sure that's going to be particularly useful because those two triangles are going to be congruent in any pair of parallelograms. But by virtue of these equal angles, there's something which is true about this parallelogram, which isn't normally true. So let's look at these angles again. Let's look at these angles 30 degrees, X degrees, and phi degrees. Is there another triangle that is not congruent to BEC, but also has 30 degrees, X degrees, and phi degrees? Okay, put the suggestions in the chat. And in the meantime, I will highlight such a triangle where there's a 30 degrees here at A. There's a phi degrees over here at C. And so if two of the angles are equal, it must be that angle ABC is equal to X. So we've got a pair of similar triangles. BEC is similar to triangle ABC. Okay, now I wouldn't necessarily always write it, but notice that when you have similar triangles, it's worth being careful to make sure that you put the equivalent vertices in the equivalent places. So we've got BEC is similar to ABC. So if triangles are similar, okay, then we know that equivalent ratios are kind of the same. So for example, we could say that EC over BC okay, in the right-hand triangle. So that's EC, which is the last two letters. And the last two letters over on the right is BC. And BC is the first and the last, so that is over AC. Okay, so the similarity condition gives me that EC times AC is equal to BC squared. Okay, let's look back at the diagram. So we've got A, E is the midpoint, C is the opposite side. B is here. And we've shown that BC squared, so this side, is AC, which is this length, multiplied by EC, which is this length. Okay. Is there any relationship between this length EC and this length AC? If you think there is, put it into the chat. Okay, and you might want to refer back to this diagram of the parallelogram where we saw that E is the midpoint of AC. Okay, so what we have here is that the AC, the whole length of the whole yellow length, is double the length EC. So we have 2EC squared is equal to BC. And so if we square root everything, we get square root of BC squared. Square root of 2EC is equal to BC. Okay, so let's draw the triangle ECB. And we've got 30 degrees. We've got X. We've got this length EC, which I'll call X. And this length BC, which I will call square root of 2 times X. Okay, so just to recap what we've done, we've started using a converse result. And we've shown that ABCD is a parallelogram. We've then identified similar triangles. Okay, and now we've reached this point. Oh, I shouldn't have used X and X. So I'll call BEC. I'll call this length. Actually, do you know what I can call this length? I can just call EC1 because I can just scale my ruler that it's 1. Okay. Excellent. I'm just going into the chat and lots of people have suggested saying that AC equals 2EC. Brilliant. Right. Now that we've reached this point, where we've got a known angle and 2 sides, is there any result from classical geometry, or is there any result from geometry that will help us find this angle X, which is our ultimate goal? So in the chat, stare at this triangle BEC, where we've got these known lengths and known angles, and tell me if we can find, if there's some result which will enable me to find the angle X. So we've identified similar triangles, and then in this stage, we found relationships between sides. fill up the chat with any piece of geometry that will allow me to relate angles and sides. Well, there's pretty much only two options, really. Okay, we have either got the cosine rule or the sine rule. Now, because we've got two angles involved, the sine rule seems like the most fruitful. So I can say that sine x over root 2 is equal to sine 30 degrees over 1. Okay. Any offers now for how to find the value of x? Well, the value of sine 30 is known. The value of sine 30 is 1/2. So we get sine of x degrees is equal to the square root of 2 over 2. And so can you now populate the chat with the value of x degrees for me? Excellent. The chat is filling up with 45 degrees. Okay, and notice that sine x equals root 2 over 2 is not uniquely specified. Okay, because it could be the obtuse angle. Okay, but we know that the question asks for the acute angle. So as the angle is acute, x is equal to 45 degrees. Okay, so here we've got the sine rule. Okay, and this is a challenging geometry problem. Okay, it's a challenging geometry problem because it's got 1, 2, 3, 4 quite meaty steps to it. Okay, I'm just going to check that everybody who's attending the webinar is happy up to this point. So if you follow this argument and if you're happy, put a thumbs up. If this argument has generated any questions, then feel free to ask them now. Oh, wow. Not only did we get a thumbs up, we got someone saying that's a nice question. Connoisseur, I'm glad you thought it was a nice question. I love this question. Now I think I might have mentioned this already. Okay. But which of these steps did I say that I think was the particular reason why I like this question and the particular idea that I wanted to introduce? Because I think there is a particular idea that is the kind of the initial kind of block of what makes this question really difficult is, I think the really difficult part is step 1. Because I think that to go from these angles to recognizing that something is a parallelogram is the biggest leap. Once it's a parallelogram, okay, I would sort of back strong candidates to identify the similar triangles, find the relationship between sides, and use the sine rule. But I think that I'm a big sort of believer that something that is often neglected in the way that geometry is taught in school are these converse results. Okay, and I would sort of strongly urge you from now on, if ever your geometry teacher or if ever your maths teacher teaches you a result in geometry, ask them, is the converse also true? Okay, we're going to look at a few more results and their converse. Okay, and we're also going to sort of link it to three dreaded words that you might see on maths exams or physics exams, especially STEP, of if and only if. Okay, so let's have a look at this question. Okay, so it says, the following diagram shows a ladder, AB, resting against horizontal ground and a vertical wall. If the length of the ladder is 10 meters, find the distance of the midpoint of the ladder M from the base of the wall O. Okay, so we're trying to find, we know that AM is 5. We know that BM is 5. We know that this is a right angle, and we're asked to find the angle X. There's lots of different ways of doing this question. Okay, and I'm going to be guided by the chat. So if you've got an idea of how to do this question, explain it very, very briefly in the chat. And whoever suggests, the first person to suggest an idea that will work, I'll do the proof in that way. And this question can be approached in a myriad of different ways. It's always difficult to know with these webinars whether to plow on so that the people that watch it on recording can just pause the video and watch on, or whether to sort of benefit the people in the webinar and actually give people a little bit of time to think. I think I should sort of prioritize the people who are here. But any thoughts of how to find this distance OM? Oh, there's 7 new messages, sorry. Oh, right, okay. The idea of using converse. People have noticed that I've said converse results a few times. Congruent triangles. Okay, AM, okay, right. Congruent triangles is what people are saying. You're good, okay? I like congruent triangles as well. So my approach of doing congruent triangles, okay, would be I'm going to draw 2 extra lines. Okay, so I'm going to draw an extra point C to complete a rectangle, and I'm going to draw the line OC. And at the moment, I'm not going to assume that that goes through. I'm not going to assume that that goes through the midpoint. Okay, but this angle MA. Angle BAC is equal to this angle OBA, because they are a right angle. So let me write this nicely, because part of the reason of doing the webinar is to show you how to write things. So let's add a point C. such that OBCA is a rectangle. Angle BAC is equal to angle OBA because they are alternate. Similarly, angle OCA, the one I've just drawn, is equal to angle BOC, and they are also alternate. Okay, so triangles A, and I'm going to call this M dash C, is similar to triangle B M dash C because the angles are the same. But because this length AC is equal to OB, wait a minute, sorry, I've labeled up my, so let's get my similar triangles right. Okay, the similar triangles are A M dash C is similar to this triangle, and the A is the B because they both have the angle that's double-headed. It's not ABC, so it's AM dash C. The M dash point is equivalent because they've got the vertically opposite angles, and this is A. But because AC is equal to BO, opposite sides of a rectangle, we have that, in fact, triangles AM-C is equal to triangle BM-O are congruent. So what does that mean? That means that AM- is equal to BM-, therefore M- is equal to M is equal to the midpoint of AC. But what we also have, okay, is we also have that OM is equal to MC. Again, by the same congruent triangles. But also OM is equal to MC. But now we've got yet another pair of congruent triangles, and I won't write it out so carefully. But ACO and BOC, they're also congruent. So because this diagonal OC is equal to this diagonal AB. Okay, so as AB is equal to OC, and M is the midpoint of OC, we have that OM is equal to 5. So this length is 5, and this length is 5. Okay. I think it's also geometrically obvious that if you just draw a rectangle, the two diagonals are bisect one another. Okay, because the triangles are incongruent. So this length is 5. Another way of doing it is you could just say that OB is the point x0. A is the point 0y. And the length AB by Pythagoras satisfies AB squared is equal to x squared plus y squared. Okay, but AB is 10, so we have 100 is equal to x squared plus y squared. The point M has coordinate half x and half y because it's the midpoint of AB. So then by Pythagoras, OM squared is equal to, so this is half x, this is half y, is equal to half x all squared plus half y all squared, which turns into a quarter x squared plus y squared. But x squared plus y squared is 100. So we get a quarter of 100, which is 25. So OM is equal to 5. Okay. Two things I want you to do is if you are happy with that argument, so if you're happy that I've proved that OM is 5, then put a thumbs up in the chat. If you've got any questions, also put that in the chat. And then the other question I want to ask is, what result, what general theorem have I proved precisely in this argument? So can you state the theorem that has been proved? So 3 things to do. Put a thumbs up if you're happy that OM equals 5. Ask any questions if you've got any questions, and then make a statement about how you would summarize in words this result, that if I draw this right angle triangle, AOB, then OM equals MB equals MA. Let's go into the chat. Ooh, lots of thumbs up. Oh, interesting. Someone said the wrong answer. Not a very wrong answer, but someone said a very interesting wrong answer. Okay, I'm gonna plow on. I'm gonna work. No one's put the right answer, interestingly. Although I think someone has implied that they know it from what they said earlier on. And someone's also said it's kind of implied that they know it from the wrong answer. So what have we really showed? So we've shown that if AOB is a right angle triangle, and M is the midpoint of AB, then these 3 points, A, O, and B, are all equidistant from M, so they lie on a circle with center M. Okay, then, so this is precisely what we've shown. Then A, O, and B lie on a circle with center M. Now we could express this in a slightly different way because we know that A, M, and B is a straight line. We could also just say that the only way that this can be a circle, you know, the only way that M can be the center and A and B can be on the center is we could say, or we could say that the conclusion is AOB is a right angled triangle implies O is on a semicircle with diameter AB. Now I'm not going to name and shame them. Okay, so there's some right answers now in the chat. So someone's put the circumcenter of a right angled triangle is the midpoint of a hypotenuse. That's a correct statement. I'm not going to name and shame them because there's no shame in it. Okay. But I'm going to quote something which is very interesting in the chat. So somebody put in the chat that the results that we have proved, and this is exactly what they wrote, they said that we have proved angles in a semicircle are 90 degrees. What is wrong with the claim of saying that we have proved that angles in a semicircle are 90 degrees? So this is a circle theorem. Okay, so you'll have proved in year 10 that if I draw a semicircle with diameter AB and the centers M, we know from year 10 that if O lies on a semicircle, with diameter AB, that implies that the angle AOB is equal to 90 degrees. Why is that not? How is that different to what we've done up here? Can anyone eagle-eyed spot the difference between this result in blue and this result in green? Okay, while the people are filling up the chat with the difference between the blue and the green, I'm just going to give you a little bit of, part of the point of these webinars is to run through questions. I'm going to prove the green result now. So with the green result, I know that M is the center. So I'm going to say let M be the midpoint of AB. I know that AM equals MO equals MB. So these three lengths are equal. So I can say that this angle MAO and this angle AOM are equal because they are the base angles of isosceles triangles. So because the triangle AMO is isosceles. I can also say that this angle, I'll call this angle theta, and I'll call this angle phi, is equal to this angle MBO is equal to the angle MOB, because triangle OMB is isosceles. So this angle is phi. And now if I look at the total angles in the triangle AOB, I've got theta, phi, and then theta plus phi. So I know that theta plus phi plus theta plus phi is equal to 180 degrees. So that's angles in the triangle AOB. But that means that 2 theta plus phi is equal to 180 degrees. So theta plus phi equals 90 degrees, but theta plus phi is the angle AOB. Okay, so this thing here is the proof of the green result. Okay, and then this argument here, either the Pythagoras or the congruent triangles, this is the proof of the blue result. Okay, let's go into the chat now and let's see if we can decide what is the difference between the blue result and the green result. Excellent. Yes. So what the person said when they said we've proved angles in a half circle are 90 degrees is a very closely related result to the one that we proved, but it's the one where the logic goes in the opposite direction. And in case I didn't explain it fully earlier, that is exactly what I mean by the converse result. Okay. So this, if you just look at it structurally, okay, the difference between the blue statement and the green statement is the way that the logical arrows point. Okay, and the proofs, notice, are quite different. Now, how might this result appear on a step paper, or what might be the kind of, you know, command word in a step paper, is that what we've proved, if we combine the blue and the green result, okay, we've shown that the triangle AOB is a right-angled triangle if and only if, so that's the statement, which means that the implication goes both ways, if and only if O lies on a semicircle with diameter AB. Okay, so you're in school in year 10. This is the year 10 circle theorem, that if you've got a semicircle, then the point on the semicircle makes a right-angled triangle. The forward result so the converse result to that is the one that we've proved in this question about the ladder. Okay, now I'm aware that as well as doing geometry, I've also introduced some logic there. So the if and only if and the proofs going in different directions. So there's actually quite a lot to swallow. So I'm just going to check that everybody's happy at this point. So if you're happy and you like this question, put a thumbs up. If you've got any lingering questions, then let me know. So just to reiterate, question 3, we proved that the distance from the center of the ladder to the wall is the same as half the length of the ladder. The theorem that proves is that the circumcircle of a right-angled triangle has its center at the midpoint of the hypotenuse. I stole that from one of you guys. Or alternatively, that O lies on a semicircle. And the answer to this question, part B, the converse result to that would have been the normal circle theorem, that if you have a semicircle, then a point on that semicircle gives you a 90-degree angle. So what we've proved is we've proved 2 implications, and in this case we have a result where the theorem also has a true converse. Excellent. Okay, we've got lots of thumbs up. Okay, I'm just going to try and gauge the atmosphere in the audience of the webinar. Who here would like a relatively straightforward question next? And who here would like a difficult question next? And who would like a question somewhere in the middle next? Okay, and whoops. I'll read through the answers. The answers in the chat have been difficult with a smiley face, difficult, difficult with a smiley face, difficult, difficult please, difficult, and then someone said, I don't mind. So we've got to go difficult. If people watching the webinar on catch up don't like the webinars and think that the questions done in the webinars are too hard, then come along to the webinars and fight the corner for straightforward. But I'm going to roll with the choice of difficult. Hopefully it's not going to be too difficult that I end up not being able to do it. Right, where's my, so I'm just trying to find my thing with the questions on. Okay, let me just move this. Sorry, I'm just struggling to get to the, this was the problem of, okay. This was the problem of democracy. Okay, so this is the question we're going to look at. No, wait 1 second, sorry. Okay. So this is a, And I mean, I think in some ways the people watching this on the webinar have the best of all worlds, because I think one would really want to process this and digest it, because this is a difficult question. Okay, this is BMO1 question, so Olympiad level, hard. So it says, let ABC be a triangle, and let D, E, and F be the feet of perpendiculars from A, B, and C to B, C, CA, and AB. And that's basically, I have made this BMO question a little bit easier because I've drawn the diagram, so you can just trust me that the diagram reflects what's said here. And then it says, let P, Q, R, and S be the feet of the perpendiculars from D to BA, BE, CF, and CA, and I've illustrated there. And then it says, prove that P, Q, R, and S are collinear. So we're trying to prove that P, Q, R, and S all lie on a straight line. And we're also trying to prove that that straight line is parallel to EF. Okay, very quickly, and I'll give you a clue that the way of tackling this very difficult Euclidean geometry problem is really thematic with what we've done today. Does anyone have any suggestions or ideas of what we might do? So people are probably thinking, oh, converse result somewhere. Now, for people here who like sort of geometry problems, difficult geometry problems, I'm going to give the biggest tip ever, and the thing which is like revolutionized my ability to do hard geometry problems, is that circles are wonderful things, because there are loads and loads and loads of geometry results about circles. Now, the sad thing you're probably saying about this question is you're probably saying, but there aren't any circles. Okay. But what there are is there's lots of right-angled triangles. Okay, now I need, actually this is a perfect point. I need the bathroom very quickly because I rushed into the house when I started the webinar. I'm going to drop that, I'm going to leave that little hint, okay, that we'd love to have circles because circles have got lots and lots of geometry theorems attached to them. But we don't, in this question, we don't have circles, but we've got lots and lots of right angles. So try and think, while I nip to the bathroom very, very quickly, try and think how to stitch those two things together. Okay. What did we see earlier? We saw earlier that every time we've got a right-angled triangle, what do we know about that right-angled triangle? We know that every time we've got a right-angled triangle, we also have a semicircle. Okay, so let's have a look at some right angles. So this right angle BE, we've got this right angle triangle, BFC. We've got this right angle triangle, BEC. So what we know is that BFC and the F and E both lie on a semicircle that has got diameter BC. Now, why does that result hold? Well, we've just seen earlier that whenever we've got a right angle triangle, there's a semicircle. Okay, and we're using this forward result. So we're using the opposite of the year 10 circle theorem. And it's kind of thematic that it's opposite, because what we're doing, because we're using the opposite direction, is we're drawing a circle that we didn't previously know was there. Okay, so what can I say? Okay, I can look at this angle CFE. Okay, so if I look at this angle CFE, so I'll try and write down a nice proof. So angle BFE equals, sorry, angle BFC equals angle BEC equals 90 degrees. So F and E lie on the semicircle with diameter BC. Oh, wait a minute. I'm not going to call this angle in here X quite yet. I'm going to call this angle up here X. So if the angle DAC is equal to X degrees by definition, then this angle down here, DCA, is equal to 90 degrees minus X degrees. And because BEC is 90 degrees, this angle here, therefore the angle CBE, I'm just doing angle chasing here, so CBE is equal to X degrees. So this angle is X. Okay, so I've just looked at this right angle triangle. To find this angle. Then I've looked at this right angle triangle to find this angle. And now I remember my initial idea, okay? And my initial idea was that every time I want to have a circle, because that gives me lots and lots of nice equal angles. So if I look, I've got this angle, CBE, that lies on a circle, but that subtends the same arc as angle BFE. Okay, so angle CBE, I'll just get rid of all the shadings apart from the ones which are relevant. And I'll do those in a different color, nice and thick. So we've got this angle CFE, and we've got this angle CBE. Subtend the same arc. Now notice, and this is very like the first question where we spotted the parallelogram, that we would have been completely stumped by this question if we hadn't used the converse result and we didn't know there was a circle there. Okay, so but what we've got now is we've got conclusion number one. We can say that angle CFE is equal to X. Okay, and I've just used the circle BC. Okay, this is obviously a very difficult question, but can I just check with people in the chat at this point? So if you were happy with this argument so far, okay, the drawing in the circle, okay, the angle chasing, and then the circle theorem, put a smiley face or a thumbs up. If you've got any questions, put them into the chat. What time does this webinar end? I started quarter of an hour late at 7:15, so I'm going to finish quarter of an hour late at 7:45. Okay, there's a thumbs up in the chat, but you can come back and watch it and catch up. But I do need to go at 7:45. Okay, as there's a thumbs up in the chat, okay, I'm going to get rid of everything except for the final conclusion, which was CFE is equal to X degrees. Okay, does anyone have any ideas about what I'm going to do next? Okay, well, there are lots of other right angles around. Okay, so for example, there's a right angle here and there's a right angle here. So if there's lots of right angles around, what do you think I can draw? More semicircles. Circles, excellent. Okay, so with this right angled triangle, DRC, and this right angled triangle, DSC, I can draw a semicircle. Okay, so the angle DRC is equal to the angle DSC is equal to 90 degrees. So R and S lie on the semicircle with diameter DC. Right, let's do a little bit of angle chasing again. We know that this angle in here is 90 minus X. Okay, looking at the right angle triangle DCA. So we know that angle DCA is equal to 90 minus X degrees. So that's angles in triangle DAC. And then if we look at the triangle DSC, we've got that this angle here, so we've got angle CDS is equal to X degrees. Okay. Can anyone in the chat tell me an angle that is equal to the angle CDS? So we've just found that this angle here, CDS, is X degrees. Can anyone give me an angle that is equal to CDS and then ideally why it's equal? Remember why we wanted to draw circles. We wanted to draw circles because there's lots of nice theorems about circles. Right, so someone suggested CRS. So CRS is this angle here. But why are they equal? Well, they are equal because they both lie on this chord SC. Yeah. So CDS and CRS, that's just our classic year 10 circle theorem. So angle CRS is equal to angle CDS is equal to x degrees, subtended by same arc. Now I'm aware we're doing geometry, but hopefully if people were happy with the first argument, they're happy again. So here we've used the converse to a circle theorem to draw a circle. And then here we've used circle theorem. So if you're happy with this bit done in red, then put a thumbs up in the chat. Yeah, good. There's lots of thumbs up in the chat. A few people are saying they need to revise circle theorems. Yeah, I mean, this pushes it a little bit beyond the scope of the actual COMPOS sheet in some ways, because that sort of stopped before circle theorems. Okay, so if people are happy, I'm going to delete all my construction lines. And I'm going to just put in this fact that CRS is equal to X. Okay, can anyone make a conclusion at this point? And at this point, it might be worth remembering what we're trying to prove. So it says, prove that P, Q, R, and S are collinear and parallel to EF. Now, we've not done the whole problem yet, but can anyone see anything that we have established? And can anyone be very, very precise about the result that establishes that? That question makes sense. Okay, I'm just going to focus your mind on the relevant bit of the diagram. So we've got a line, and then we've got two lines coming off that line. And we've got two equal angles. And this is very thematic of this evening. What does this diagram look like? What very, very familiar diagram does this look like? Try and ignore all the other lines apart from those two. Okay, so if I draw a line and then two lines coming off it, and I draw two equal angles, what bit of geometry do you think? What very familiar bit of geometry do you think is? I'm going to talk about if I've drawn this diagram. Where have you seen this diagram very, very many times? How would you describe these angles? So we would describe these angles as corresponding. Okay, and if these lines are parallel, then the corresponding angles are equal. Now, what we've shown here is that the corresponding angles are equal, but that means by the converse result, we can conclude that that these lines are parallel. Okay, so CRS and CDS are equal corresponding angles, okay, so what we can say is that FE is parallel to EF. And so this is the converse result about parallel lines. Okay. If people are happy with this purple section, so how I've gone from the equality of these two angles to these two lines being parallel, put a thumbs up into the chat. Okay, so it's just the normal result about corresponding angles, but in reverse. Okay, so we have done, so what we've shown so far is we've shown that RS and EF are parallel. Okay, what do you think I'm going to do next? I'm going to get rid of all of this, but I'm going to just keep what I've shown. So I know that EF and RS are parallel. Okay, well, what I want to do, okay, is I want to show that the other bits of this line, PQ, QR, and RS, are also parallel to EF. Okay, but what I've got is I've still got more right-angled triangles. Okay, so the next right-angled triangle I would look at would be this one. Okay, and if you repeat exactly the same sort of argument, DPQ is DBQ, so we get another angle that is equal to X. Okay, and if you follow it through, you'll get lots of other lines that are parallel to FE, and if you stitch all of it together, then that completes this problem. Okay, so that's we're pretty much I won't finish all the steps, but we're pretty much out of time. What have we done? What have we done? How do we prove collinearity though? That's a very, very good question. So if I draw a straight line, and we've got this angle here is x. If I can show that this angle here is 180 degrees minus x, then we can show collinearity. The other way that we can show collinearity is if we can show that two lines, if I can show that AC and BA are parallel, then BAC are collinear. Okay, and that is the same as if I've got parallel lines, as if I could show that, and these are the wrong letters, but if I could show that angle NAC is equal to angle MBA, and MN and AN and MB are parallel, then I could show that BA and AC are parallel by the converse to corresponding angles, and that would be enough to show collinearity. This little pitch that I'm making is that for challenging geometry problems, like the one we did at the beginning, quite often are challenging because they use familiar results in the order that you aren't expecting, which is part of the reason I wanted to introduce converse results. The other thing which I wanted to introduce, which I wanted to make sure I introduced, because I know that this is something, again, which causes problems, is that on step papers, people that have to do step quite often start to have a bit of a phobia if they see an if and only if. And I wanted to drill down into what if and only if meant, and to show that an if and only if is really two things. It's two different arguments. Splits into doing two things. Okay. It's 7:45, so I'm going to just go back to the Zoom call. I will write up or type up the end of this question and share that. But I'm just going to go back to the Zoom call for any final questions, comments, reflections. And then if there aren't any, then I'm going to say bye-bye. So I'm just going to pull up the video. Okay, so lots of geometry tonight. Hopefully you've seen some interesting problems. Does anyone have any final comments that they want to make? Oh, someone said tonight's problems are fun. That always makes me happy. So there's a question which says, are converse results something we should use a lot in this assignment? Not really. This is a little bit of an extension, but there are, what I did put in the problem sheet was a couple of ifs and only ifs. And that's the same as proving the theorem and its that's the same as proving a theorem and its converse. Super. Oh, people are saying the problems are fun. I like them fun. I love geometry. Okay, so I'm going to say thank you to everybody. Good night, and I will see you for another webinar. I can't remember if it's next week or in a couple of weeks' time. But enjoy the geometry sheet, and see you soon. Okay, I'm going to end the meeting for all. Bye-bye.